x squared plus x plus 1. Perfect. And give us an interval. You don't have to start at 0. We can illustrate with anything.
2 to 8.
2 to 8. Awesome. So we want to find the exact area using the limit of the Riemann sum. Whenever we're asked to use the limit of the Riemann sum, we have 3 preps. We cannot directly start the sum before we work on these 3 preps. So, what is the first prep?
Finding the delta.
Delta x. So 8 minus 2 over n. So delta x is 6 divided by the number of subintervals. Perfect. What is the second prep?
Finding xi.
Excellent. xi. Remember, this time it starts at 2, not at 0. So 2 plus I delta x. This is always the same. The beginning plus I delta x. If it's 0, I have 0 plus I delta x. If it's 2, I have 2 plus I delta x. I replace delta x. So I have 2 plus 6I over n. What is the last prep before I put everything together?
Find fxi.
F of xi. Very good. F of xi. So this is my xi, and this is my function. So I have in here 2 plus 6I over n squared plus 2 plus 6I over n plus 1. I have to simplify this to the bone before I do anything else, before I put the limit of the Riemann sum together. This has to be the simplest possible form before I even think of doing anything. So I guess there are other methods if you find an easier method, but this is what I recommend. Remember, a binomial squared has 3 terms. The first term squared, 4, plus 2 times 2 is 4, times 6 is 64I over n, plus 36I squared over n squared, plus 2 plus 6I over n plus 1. And now I will put everything in descending order and clean it up. I'm interested in I, of course. This is first. Now, this plus this is 70I over n. And this plus this plus this is 7. Only now I'm ready for the exact area and the limit as n approaches infinity from the sum from I equals 1 through n from delta x. We cannot forget delta x, 6 over n. You can already put it in front if it's better for you. 6 over n times all this. Oops. Okay, now we're going to use those 2 properties of the sigma notation. So first I copy the limit. I can move this in front. And now, it's a lot of writing. If we can cut back a little bit, it will be great. So this is out. So I have the sum of this, but I realize that this is a constant. So 36 over n squared times the sum of I squared. Now the sum of this, but I realize that this is the constant. So plus 70 over n, the sum of I. Plus 7, or any number, is 7 times 1. So when I apply the sum to the last term, 7 goes in front. The sum of 1. Of course, from I equals 1 through n. From I equals 1 through n. From I equals 1 through n. So let's stop for a moment and let me explain this step one more time. This is in front. And now I have one of the properties, the sum of AI plus BI plus CI is the sum of AI plus the sum of BI plus the sum of CI. Those three generic terms. But when I apply the sum here, just to try to cut back on writing, I see that this is a constant that it goes in front. And that's the only piece that depends on I is I squared. And I have an answer for this. Then when I apply the sum to the second term, I realize that 70 over n goes in front, and I have the sum of I. And here I have to remember that 7 times 1. 7 goes in front, and the sum of 1 is what I know. So all these will be replaced. This will be replaced by n plus 1, 2n plus 1 over 6. This will be replaced by n plus 1 over 2. And this will be replaced by n. And then everything reduces to finding a limit. But I still have calculations to make, to work on. But let's stop again for a moment and see if this is clear or there are questions. See, everything rests on these 4 identities. We didn't have the I cubed, but the 4 identities. Everything depends on that. That's why we don't have these identities for tangent, secant, arctangent, and so on and so forth. We don't. But we have them for these. So now I have to work on algebra. From this point on, it's all algebra. Finding the least common denominator, simplifying, blah, blah, blah. Okay, so limit n approaches infinity, 6 over n. 36 over n squared times this. Plus 70 over n times this. Plus 7n. Okay. So now let's see how we simplify and how we get this limit. I will simplify by 6. And I will simplify 1n from here with 1n from here. So the denominator here is still n. Here I will not simplify because I still need the same denominator, but I will simplify by 2. And this one needs to be multiplied by an n because it doesn't have a denominator. This one has denominator n, this one has denominator n, but this one doesn't, so it has to take an n. Okay. Yes, the calculations are cumbersome. Yes, it's a long problem. I agree. It would have been a little bit easier, but I wanted you to see at least one example in which the interval does not start at 0. So this is very important to see. So limit as n approaches infinity, 6 over n patiently waits, n in the denominator. And now watch me run out of room. I will always do that. Okay, so I do have a 6 here that needs to be multiplied here. So this product, easy to remember, 2n squared plus 3n plus 1. But I need to multiply by 6. 6, 2n squared plus 3n plus 1. Plus 35 times n squared and 35 times n. So 35n squared plus 35n. And plus 7n squared. As I promised, I ran out of room. Okay. Finally, almost there. N times n. N squared. 6 stays in front. 6 times 2, 12n squared plus 18n plus 6 plus 35 plus 7, 42, n squared plus 35n. Okay, so limit n approaches infinity. 6, 12 plus 42, 54, n squared. 18 plus 35, what is it? 53, I think, plus 6 over n squared. At this point, we should already say, I see it's the same degree over same degree, it will be 6 times 54. But let's say we don't see that. So I can take 6 in front of the limit. I differentiate because it's infinity over infinity. I get 108n plus 53. I get 2n. Again, it's infinity over infinity. When I differentiate, I get 108 over 2, which is 54. I have the 6 times 54, and that's it. 328. What is this? Well, some units squared, whatever it is. You chose a good one, Sean. It was long, but we needed to see it. And the numbers were not too ugly. That's why we studied L'Hopital's rule. That's why we studied limits. One reason is this. And now, I know I have like a few minutes left, so I just want to explain a different way of calculating this, which is how we're going. Yes, any question, please. Colby, go ahead.
I was just struggling to keep up and was flipping and writing, but how did we get 2n instead of n squared on the bottom of the last part?
But when I differentiate the top, I bring 2 down.
Oh, that's where you apply it.
And I have to differentiate this, and I get 2n. When I differentiate again, I get 108 over 2, which is 54. But is the mechanism clear? Do you have any questions on the steps? Let's review the steps one more time. For any function, we can find the area, but we need 3 preps. First, we have to have delta x. Then we have to have xi, which is 2 plus I delta x. If it's 0, it's 0 plus I delta x. If it's 10, it's 10 plus I delta x. Then, once I find this, I plug it in the function because I need f of xi. What does this mean? When I is 1, I'm looking at the first rectangle. When I is 2, I'm looking at the height for the second rectangle. When I is 3, I'm looking at the height for the third rectangle, and so on and so forth. That changes. For each rectangle, there is a different height. That's why I need f of xi. For the first interval is this height. For the second interval, maybe this. For the third interval, maybe this, depending on which interval I'm in. I clean this up completely. And then I write that the exact area is the limit of the Riemann sum, the sum of delta x, which can be put in front. It does not depend on I. Anything that does not depend on I can be put in front, but I have to do it carefully and legitimately. So this goes in front because it's a factor. If it's plus, you cannot move it in front, right? But it's a factor, of course. It's base times height. Base of the rectangle times the height. This is the base, this is the height. So this is a factor, goes in front, and when I apply the sigma notation to the first, I realize that this is a number, it goes in front, so I have I squared. When I apply the sigma to the second, I have 70 over n in front, and I apply sigma to I. And then always remember, a constant is 7 times 1, or 10 times 1, or negative 3 times 1. So that number goes in front, and the sum of 1. These three were given to us. We have 4 identities to remember. So then all this will be replaced by this expression. All this will be replaced by this expression, and this will be replaced by this expression. Once I do that, from here on is just algebra. Till I get to differentiate, when I simplify it completely, I realize that it's infinity over infinity. I differentiate the top, I get this. Differentiate the denominator, I get this. I differentiate again, 108 over 2, 54 times 6 is this. Okay, so now...
I can't remember the exact starting problem, but you did u squared because that's like units squared, right?
Yes.
Or is that something?
Yes, because it's area.
Okay. Oh, yeah, it is.
Only because it's area. So this is the area. Yeah. Good. So we do have a different way of determining the exact area, limit as n approaches infinity, from the sum from I equals 1 through n, delta x f of xi. And this time we are going to use s, but a stretched s, still for sum. A very stretched s. Remember the interval that we chose was a comma b. And then I'm going to use that word in a minute. So it's a stretched s, which means the same thing. So basically this is these two combined. And this piece is the same here. F of x dx. From a lower limit of the integral symbol till the upper limit of the integral symbol. So this is called, we know that this is the limit of the Riemann sum, but this is the definite integral from a to b from f of x dx. They mean the same thing, they are the same thing, but it's not going to take us 3 pages to do this. But I have to explain how we calculate that. I explained so far how we calculate this. We get the delta x, we get f of xi, we plug it in, we multiply, we use the sigma, those 4 identities, we apply the limit, blah, blah, blah. How do we do?
Sorry, but
no.
Are delta x and dx the same thing?
Always.
What was the one that was almost, but not quite?
Yes, the delta y, almost dy.
Oh, so the x.
But the error, the error is always the same. Yes.
Okay.
Yes, but here, very good point. Thank you for reminding me. Here we do not, although they are the same, we never use delta x here. We only use delta x in the sum, and we use dx in the integral, in the definite integral. Definite because it has limits of integration. This is the upper limit of integration. Here was the lower limit of the summation, and the upper limit of the summation. The upper limit of the integration of the integral, and this is the lower limit. Not LIM, but the starting point, if you want, lower limit of the same thing. How do I calculate this? The requirement here is crucial. The function must be continuous.
So when we have this